Oh, thanks. I was right here yesterday at the end of the hour, and it was right at 2:10. I said, okay, yeah, that's enough for today. But we had seen this yesterday. The fact that the nitrate ion has one of the N to O bonds is a double bond, and then the other two are single bonds. When the bonds in NO3, though, are analyzed, it doesn't show one being shorter than the other two. And when you have a double bond, it should be shorter than single bonds. But this thing, when it's analyzed, doesn't. It shows all three bonds are the same. How can that be when one of them is a double bond? Well, what we think that atoms or molecules like this do, we think that it actually is a hybrid or a combination of the three of those blended together, in which instead of having two bonds that are single and one that's double, nitrate actually has 1 1/3 bonds for each. We call that resonance. And that's what is reflected when the bonds are analyzed for their length, is that they're all the same. And they're all about the length of 1 1/3 bonds. So that gives rise to this idea of resonance. I don't think you saw this at all yesterday, did you? Okay. So yeah, when you have a structure that it has, it's got one double bond that could be in more than one place. It gives it what we call resonance. Now, I don't know that it's necessary to draw this. I don't think you have to. This is what I showed on the previous slide. This is the way that we represent something that has resonance, though. You draw all the possible structures, and then you connect them with the double arrows. And the double arrows indicate that it's not any of those three at any instant. It's that all three of them combined is the actual structure of this thing. This gives rise to something that we call the bond order. The bond order on this is really essentially how many bonds are between the N and each oxygen. It's 1 1/3 or 4/3. And bond order is calculated like this. It's just the number of bonds divided by the number of possible locations for each of those bonds. So there's 4 bonds that can go at 3 different places. It's 4/3. So the last thing about resonance, as I was just saying, yeah, so we don't see one short and 2 longs, and then alternating. It's just a combination of those 3, an average. Now my next slide I'm not going to spend a whole lot of time on. It was where I intended to start the hour today, but we didn't get to this yesterday, so we had to start with this. We all good? Okay, so for this one, I intended for you to do this, but I'm not going to have you do it. Nitrite ion, I just want to show you this. This was going to be a follow-up from what we did with the resonance. This is what the nitrite ion looks like. Turns out that there's two resonance structures for nitrite. So the double bond could be either on the oxygen on the left or the oxygen on the right. The bond order, what's the bond order of the nitrite ion? How many bonds between the N and each O? It's 3/2. Yeah. There's 3 bonds present, 2 there and 1 there, and then there's 2 different places they could be. So we would consider the bond order of this one to be 3/2, or 1.5. You okay with that? Okay, now what we have to spend most of our time on today is shapes of molecules. We've got to talk about all of the possible shapes that molecules can have. Now, you learned about shapes of molecules in Chem 1. A lot of these are going to come back to you. But there's a number of shapes that we haven't learned yet because they involve exceptions to the octet rule. So, yeah, you'll have some new shapes here. They're good, though. I think it's fun. Get some new stuff. All right, may I move on? So yeah, we're going to kind of organize how to come up with the shapes by what we call the coordination number. The coordination number is going to focus on the central atom. We always look at the shape around the central atom. And its coordination number is the number of bonded atoms plus lone pairs. That's how we're going to come up with a coordination number. How many bonded atoms on the central atom and how many lone pairs, and then add those together. Now the first one that we're going to do, and we didn't spend a lot of time yesterday on dot structures. I'm not going to just keep hammering and having you do dot structures. It just slows us down. So I'm going to give you all these dot structures. Just ask me if you're not sure how I came up with it. And we'll see if we can come up with the shape of it. Now the shape, remember, is based on this theory that we have in chemistry. You've seen this theory before. I hate the fact that we spell it differently than we pronounce it, but everybody in chemistry call this Vesper Theory. Even though the S and the E are not in the right place to call it Vesper, that's what it is. Vesper stands for valence shell, electron pair repulsion. And what this says is, this is how we come up with a shape. All shapes that we come up with are based on this theory or assumption. The theory that around the central atom, the electrons that are making bonds or even in lone pairs try to spread as far as they can get from each other because electron pairs repel each other. Electron pairs repel. So electron pairs don't like to be real close to each other. They're going to spread out as far as they can get from one another. And all shapes are based on that. So if we have carbon dioxide has the dot structure that looks like this. We actually did this one yesterday. The carbon has a bonded oxygen on one side, the bonded oxygen on the other side. How would the carbon and the two oxygens arrange themselves so that these electrons and these electrons are as far apart from each other as they can get? Well, they would spread out just like it's drawn, 180 degrees from each other. They can't get any farther apart than that. So now for each of these I have a computer model. Yeah, there's my carbon dioxide. And you can see this shows its shape. It's a linear shape. And the angle there between the carbon and the two oxygens is 180 degrees. So that's our only example of a coordination number of two. There are other examples of coordination number of two, but sometimes we'll have other possibilities with lone pairs for different coordination numbers. That's it for coordination number of two. All coordination number of two is going to be linear. We're going to move on to the next one, which is coordination number of three. You're going to recognize all of these shapes as well. The first one is H2CO. H2CO has a carbon in the middle with a double bond to an oxygen, then two single bonds to hydrogens. How do these atoms arrange themselves? Keep in mind, we always base our assumption about shape on Vesper theory. The fact that these atoms are all going to spread as far as they can get from each other. And when they do that, it's going to make this shape, where the carbon in the middle. Now, one of these is a double bond, but the number of bonds doesn't matter. The fact that carbon's bonded to three atoms is all that matters. The fact that one is a double is fine. So what shape do we have here? It's a triangle shape, right? And notice all the atoms are in the same plane. It's a flat molecule, so this would be considered trigonal planar. Now, we have to mention that it's planar because you can't just say triangle, because there actually is one shape, and you've heard of it before, where they're not all in the same plane. So we do have to mention when it is planar. In this case, it is trigonal planar. The angle of these bonds are all the same. They're all 120 degrees. Here's a model of that one. Notice that the molecule isn't totally symmetrical because the oxygen is this big bulky thing compared to hydrogens. So, but still, you have 120 degrees between each of those bonds. Yeah? We have another coordination number of three molecule. This one's going to have a lone pair on the central atom, which is going to make it a different shape than the one before. HNO has nitrogen in the middle. And by the way, I'm going to be honest with you, I don't even know if this molecule exists. I think it would be called Hypo nitrous acid. It works on paper, so I guess it's good enough. But it may not even be a thing. The dot structure of HNO looks like this, where the N is double bonded to the oxygen, single bonded to the hydrogen, and the N also has a lone pair on it. We always look at what is happening around the central atom. So the central atom is the nitrogen, and the nitrogen has two atoms attached to it and a lone pair. That's what gives it a coordinate.